Hey everybody, this is Larry. This is May 25th, so the 25th day of the Leetcode challenge. Hit the like button, hit the subscribe button. Let me know what you think, how did you do, and let's get at uncrossed lines. We write the integers of a and b on two separate horizontal lines. Now, we may draw connecting lines. A straight line connecting two numbers a sub I and b sub j such that a sub I is equal to b sub j. The line we draw does not intersect any other connecting non-horizontal line. Are there horizontal lines? Note that connecting lines cannot intersect even at the endpoints. Each number can only belong to one connecting line. We turn the maximum number of connecting lines we can draw in this way. Can we draw like going around or something? I guess not, because that would make it really hard. But yeah, so the first thing that I think about this is dynamic programming, and it probably is. And then the second thing I do is um, I look at the n's and m's, and n's and m's are less than 5 or 500, so it should be okay, right? Because n squared is what I'm thinking of. And this is a very standard dynamic programming problem. I believe it was even the reason, some with a twist, but uh, it was the recent Q4 on a Leetcode contest, for example, similarly. But the idea is that you're given two sequences, and the question that you should ask is, does ordering matter? Does it matter? And if it matters, then can we do things one digit at a time or one number at a time of the sequence, right? And I think in this problem you can. And some of this requires playing a lot around with the constraints in your head, or just drawing it out with paper and pen. I actually have a notebook here. I don't think I need it for this problem, but because I've solved similar problems before. But if you haven't, then maybe draw it out to be like, okay. So the idea is that what I got from reading this problem is when I draw, say, this on example 1 from a 4 to a 4, that means the 2 on the bottom gets cut off, right? That means we don't use it at all. So in that sense, it does create an ordering that means that you can only consume one at a time. One item, or you can consume one item at a time, because once you throw away an item, you will never need to use that item again, whether it's connecting or not connecting. And then now we break down the cases to, well, okay, one item at a time. How do we know if we can connect them? Well, we connect them when they have the same number. We draw a line, and if we don't, then we could just quote unquote brute force by throwing away the left item, or by left I mean an item from list A, and then we also try throwing an item from list B, and then we do that recursively to start with, top-down memoization. You could convert this to bottoms up, and you could also, and it seems like in this problem you can do the space optimization trick. I'll have a link below on how to do that. But today I'm going to just do the top-down memoization. Cool. And usually people will see that I use LRU cache, which is a Python library that helps a little bit with the memoization, but only on the implementation side. But I found that no, it's a crutch, right? You really need to understand dynamic programming for interviews and competitive programming in general. And even though, yes, you can slap LRU cache on a function and see if it works, ideally you understand the space-time complexity. And space-time complexity sounds like some kind of sci-fi thing, but in any case, you have to understand the analysis, and when you do, then you can do things in a number of ways. And if none of that makes sense to you, then you probably don't need to, because this is a very Pythonic or Python-specific trick as an implementation. But I urge that, it's all about the fundamental understanding of these problems. So definitely, I'm going to go over it, so don't worry. But yeah, try not to use LRU cache if you're starting out. But okay, so let's get started. Let's write the recursion line, which is, let's just call it get max. Naming is a little tough for me, but you can figure it out. And then now, let's start with A index and B index, right? And then now let's just say n let's say NA is equal to length of A, and B is equal to length of B. Well, what's the base case, right? For me, the base case is if A index is equal to NA, that means that we ran out numbers on NA, or equivalent, if we ran out of numbers in B, then we can just return 0 because you're not matching anything anymore, right? So that's your base case for the dynamic programming, or just recursion in general for now. And then now let's try to get the best thing, right? Let's start best with 0 because the best you can do is going to be 0 no matter what, I suppose. And then now there are a couple of, as we talked about, we could either throw away the left index, and what that means is that we just throw it away. Don't really worry about it, right? So we take the max of that and get max of A index plus 1, B index, because this means throwing away the first index, or the A. We move on. If you look at the numbers, then we just consider the subsequence of A, right? And then now we do the same thing with B. So that also is the same understanding. Is basically just to illustrate it a little bit more. Let's say we have two lists. Let's take a longer list. So what we're doing is, let's say we have some random index in the middle. So here, this is saying, okay, we don't need to consider this 5. Let's move this to 1. And here it's saying, well, it's still at 5. Let's skip the 2 and move it to 1. Wow, that's coincidental, but yeah. And then now the other case, and we only get to cross a line if they're the equal. So if A sub A index is equal to B sub B index, then we can do the best that way. Get max of A index plus 1, B index plus 1, because 1 is the number of lines crossed, and when we cross one line, we get plus 1 for the additional line. And then now we just have to return best. So we haven't done the memoization yet, don't worry, I'll get to it. And then now we just do get max of 0, 0, counting from 0, 0. You can also go the other way. This is an example where this is symmetric, meaning you could go backwards and forward and you get the same answer. So you could actually also go from N A and B and go down to 0 if you prefer it that way. And that way it's also easier, bottoms up. So, but it's mathematically equivalent. But yeah, now let's test the test cases. So I don't expect this to pass, or I expect this to pass in correctness, but it should give us a time limit exceeded. But I just wanted to kind of show show that it should be okay. I think this should maybe run fast enough for these small cases, and it looks good. Yeah, and the reason why we can't forward away the things on the numbers is because once you cross a line, like in this case again, if we cross 4 of the 4, then you can think about, well, you can't cross line going backwards, right? That means everything to the left of the upper 4 and the bottom 4, including the 4s, are gone, right? So now that's how you can think about these subproblems. Cool. So yeah, so now I definitely expect this to be time limit exceeded, and we can even play around with a big number. Was it 500? We don't even have to go 500, I don't think. Let's just do, okay, that's 5, 10, 20, 30, 40, 50, and I think this is probably good enough for it to get a time limit exceeded. And also, and one thing to construct is to figure out what our answer should be for these, right? For this one, it should be obvious that it should be 50 because, or for, however number of ones, because we just match up the ones at a time. And for this case, we get time limit exceeded as predicted, but that's because we didn't add the memoization. So how do you add memoization, and how do you do this analysis, right? Well, maybe I'm doing this a little bit backwards, but the way to think about this analysis is that, well, how many states are there? And by states, I mean how many possible inputs are there to this function, right? Well, A index can go from 0 to n sub A. B index can go from 0 to n sub b. I'm going to type it out just for visualization. So A index can be from 0 to n sub a, well, minus 1. Well, I guess it could be n sub a, but then, or na, sorry, but then it just returns 0. So let's actually call that. And then B index is equal to 0 to nb, right? And because these two indexes don't depend on each other, so the number of possible states is just na times nb, technically na plus 1 times nb plus 1, because 0 to na inclusive is na plus 1, and same for nb, right? So this is the number of states. So if we were to store one result for each of these na plus 1 times nb plus 1 cells, then it will have na times nb space. So that's how we think about it. And then from that, we're like, okay, that's actually a good enough, or like we have enough memory for 500 times 500. So let's create an array to that effect. And then the other thing that I would also say is, while that we're here, what is the running time complexity of this, right? Well, for each state, for each possible input, and that's what we mean by state in this case anyway, we're doing at most 3 or 4 operations, depending on if you count this one bit. So a constant amount of operation. So, and the O of n, the big O notation will hide that, in that it will give you O of n sub a times n sub b space. So okay, so now that we know that, let's create a cache. So now let's create a dynamic programming. I name it DP just so that you remember. You can call it cache. You can call it whatever you like, right? Let's just call it. Let's just do -1. It doesn't really matter because we'll do it another way. Times nb for in range na. So this is just to actually this is a little off by 1. Oops. So this creates a matrix of nb or na plus 1 times nb plus 1, right? And that's just for the ease of doing this. Let's just also have a scene array, which is the same as this, but just a Boolean. Let's just say force. So maybe scene is maybe let's just say calculated. Maybe that's an easier way to figure to name it. And here, let's say we ignore the base case. So if you ignore it, you don't actually need the plus 1, but that's fine. It's a little bit extra space. We don't need to worry about it for now. But now, let's say the base case is not true, and in this case, it cannot get out of bounds. Let's just say if calculated of 8 index, b index, that means if we already calculated the results for A index, B index, then we return dp of A index, B index. Okay, so that's good, but if we run the code, it still doesn't work because we don't populate the cache. I call it cache because that comes up inside. And that would still give us time limit exceeded, right? Or it should. If it doesn't, then there's some craziness going on in the world. And then now, but that just means that at the end, we just need to cache it. So now we can just do calculated 8 index, B index is equal to true. And then we set the dp is equal to best. And now with about 4, 5, 6 extra lines of code, this one's brazenly 44 milliseconds. So now let's submit it and wait. Well, before I submit it, let's actually let's test some additional base cases I just want to focus on, like with empty arrays on either one, though I think it should matter. And I think that may be the only edge case that I need to worry about. Oh, okay, so actually, no, it doesn't, does it tell me that? Oh, actually, no, I missed the constraints, but that's great. Let's just make it 1 just to kind of test that. That should be okay. Yeah, so now let's submit. Cool. So yeah, so this is how you solve the dynamic programming problem with respect to taking the top of icon ticking the top or the front of the list of two different lists. You can do that when you recognize the pattern that once you processed a number, everything before that doesn't matter anymore to you. And if you have that situation, then you can do this kind of work. And again, let's talk about the space-time complexity. So the space, as you can see, we allocate O of n, NA times NB space, two of them, but that's okay. And time, as we talk about again, because we have NA times NB possible inputs to get max, and each of them does O of one operation. We do O of n sub, or sorry, NA plus NB running time. Yeah, and this is a very standard problem in an interview. Maybe it's a little bit on the harder side, but I could see it coming up. And on competitive programming, this comes up all the time, literally. Or at least maybe not doesn't come up all the time, but it's expected that you get there, and it comes up not as core of the problem, but it just comes up all the time. Yeah, that's all I have for this problem. I think one additional thing, given I said at the beginning of the hour, there are a number of ways to write this part with the dynamic programming. Another way is LRU cache or using sets or dictionary or something like that. And feel free to experiment with that. But for this one, for today, I wanted to be really explicit about the space-time complexity. I think with LRU cache and just putting things in sets or dictionaries, that's fine once you understand how the space complexity is determined and once the running time complexity is determined. Because here, it's very clear that, well, I hope it's very clear that it takes n of A times n B space. But when you use LRU cache, sometimes you just like, oh, it's magic and it's great. But in an interview or on harder competitive programming problems, you may not feel like it's so great when you write a function in a way such that you didn't really do the analysis, and then you just slap on a thing, and then time limit exceeded or memory limit exceeded, and you're like, well, I guess that's all I can do. And you maybe either needed a better algorithm to begin with, or you just wasted a lot of time coming up with this, right? So, and that's something that if you had just spent, if you really understand the problem, then you only need to spend like, I don't know, 30 seconds to analyze it this way, and then you'll know not to take that approach. Cool. But that's all I have for today. Hope you have a great day. Hope you have a great weekend. Hit the like button, hit the subscribe button, make my day a little bit better. And I will see y'all tomorrow. Bye-bye.